A RESTful API, Representational State Transfer API, is an architectural style for designing networked applications that communicate via HTTP. It's widely used because of its simplicity, scalability, and stateless nature. For more tech interview materials, please go to our website at bowsy8.com. How a RESTful API works, step by step. 1. Client makes a request. A client, web app, mobile app, or service sends an HTTP request to the API endpoint, URL. Example, get https://api example.com/users/123 retrieves data for user 123. 2. Server processes the request. The server processes the request based on the HTTP method and endpoint. Common HTTP methods: get, retrieve data; post, create new data; put/patch, update existing data; delete, delete data. 3. Response generation. The server returns a response with a status code and data, often in JSON format. Status codes indicate success or error. 200 OK, successful request. 201 created, new resource created. 400 bad request, invalid input. 404 not found, resource not found. 4. Stateless communication. Each request is independent and contains all necessary information. The server does not store client state between requests. Major components of a RESTful API. 1. Endpoints, resources. URLs that represent specific resources or data. Example, /users, all users. /users/ID, specific user by ID. 2. HTTP methods, verbs. Define the action to perform on the resource. Get, read a resource. Post, create a resource. Put/patch, update a resource. Delete, remove a resource. 3. Request and response. Request contains the endpoint, HTTP method, headers, and optional body. Response contains the status code, headers, and data, often JSON. 4. Headers. Metadata for requests and responses. Examples. Content type specifies data format, e.g., application/JSON. Authorization provides authentication info. 5. Statelessness. The server does not retain any client context between requests. Each request must contain all necessary info, like tokens for authentication. 6. JSON, JavaScript object notation. A lightweight, human-readable data format for exchanging information. 7. Status codes. Provide feedback on the request outcome. 200 OK, successful. 201 created, resource created. 400 bad request, client error. 404 not found, resource not found. 500 internal server error, server issue. 8. Authentication and security. Methods to secure the API, such as API keys, tokens included in requests. OAuth, secure authorization. JWT, JSON Web Tokens for stateless authentication. Key benefits of RESTful APIs are: 1. Scalability. Stateless nature allows for easy scaling. 2. Flexibility. Works with various programming languages and platforms. 3. Simplicity. Easy to understand and implement. 4. Performance. Efficient due to lightweight JSON format and stateless communication. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com. A domain name system, DNS, is a fundamental part of the internet that translates human-friendly domain names, e.g., www.example.com, into IP addresses, e.g., 192.0.2.1, that computers use to identify each other on networks. For more tech interview materials, please go to our website at bowsy8.com. How DNS works, step by step. 1. User request. When you type a domain name, e.g., www.example.com, into your browser, the browser needs to find the corresponding IP address to access the website. 2. DNS query initiation. The request goes to a recursive DNS resolver, usually provided by your ISP or a public service like Google DNS or Cloudflare DNS. 3. Recursive query process. The resolver queries several DNS servers in sequence to find the IP address. This process involves root DNS server. The resolver first contacts the root server, which knows where to find top-level domain TLD servers, e.g. .com, .org. TLD DNS server. The TLD server points to the authoritative DNS server for the specific domain, example.com. Authoritative DNS server. This server holds the IP address for www.example.com and returns it to the resolver. 4. Returning the IP address. The recursive resolver returns the IP address to your browser. 5. Website loading. The browser uses the IP address to connect to the web server hosting the website and the page loads. 6. Caching. To speed up future requests, the resolver temporarily stores, caches, the IP address for the domain. Major components of DNS. 1. Domain names. Human-readable addresses, e.g., www.example.com. 2. IP addresses. Numerical addresses that computers use to identify each other, e.g., 93.184.216.34 for IPv4 or 2001:0DB8, 1 for IPv6. 3. DNS resolver, recursive resolver. A server that receives a DNS query from your device and performs the full lookup process on your behalf. 4. Root DNS servers. 13 logical root servers worldwide, e.g., a .root-servers net to root-servers.net. They direct the resolver to the correct TLD server. 5. TLD, top-level domain, servers. Servers managing domains ending with extensions like .com, .net, .org, or country codes like UK or .da. 6. Authoritative DNS servers. The final source of truth for a domain's IP address, maintained by domain owners or hosting providers. 7. DNS records. Different types of data stored in DNS, such as a record, maps a domain to an IPv4 address. Quad A record, maps a domain to an IPv6 address. Name record, alias for another domain. MX record, mail server information. NS record, specifies authoritative name servers. 8. Caching. Temporarily stores DNS query results to reduce lookup time for frequently accessed sites. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com. A rate limiter is a mechanism used to control the rate of requests or operations to prevent misuse, overloading, or resource exhaustion in systems like APIs, servers, or applications. It ensures fairness, protects system stability, and enhances security. For more tech interview materials, please go to our website at bowsy8.com. How rate limiter works. 1. Incoming requests. A client sends a request to a service, e.g., an API endpoint. 2. Rate check. The rate limiter checks how many requests have been made by this client in a specific time window, e.g., 60 requests per minute. 3. Decision. If the client has not exceeded the allowed limit, the request proceeds. If the client has exceeded the limit, the request is rejected with an appropriate response, e.g., HTTP status code 429 too many requests. 4. Enforcement and reset. The rate limiter keeps track of request counts and resets counts after the specified time window. Major rate limiter algorithms. 1. Token bucket. A bucket is filled with tokens at a constant rate. Each request consumes a token. If the bucket is empty, requests are denied. Example: if the bucket holds 10 tokens and refills at 1 token per second, you can handle up to 10 bursts of requests instantly and then 1 per second thereafter. 2. Leaky bucket. Requests flow into a leaky bucket and are processed at a fixed rate, like water leaking from a hole. If the bucket overflows, excess requests are dropped. Use case. Ensures a steady output rate regardless of bursts in traffic. 3. Fixed window counter. Counts requests within a fixed time window, e.g., 100 requests per minute. If the limit is exceeded within that window, new requests are rejected until the next window starts. Limitation. Can allow bursts at the edges of time windows. 4. Sliding window log. Maintains a log of timestamps for each request. The limiter counts requests within a rolling, sliding, window, e.g., last 60 seconds. Benefit. Offers smoother request distribution compared to fixed windows. 5. Sliding window counter. Similar to the fixed window, but divides the time window into smaller segments and applies weights to them for a smoother sliding effect. Major components of a rate limiter are 1. Counter/token store. Keeps track of request counts or tokens. Can be stored in memory for a single server or distributed stores like Redis for multi-server deployments. 2. Time window. Defines the period over which limits are enforced, e.g., 60 seconds, 24 hours. 3. Policy configuration. Specifies the rules such as limit, maximum requests allowed, e.g., 100 requests/minute. Reset interval, when the count resets. Burst capacity, number of requests allowed in a short burst. 4. Enforcer. Decides whether a request should be allowed or blocked based on current counts or token availability. 5. Response handler. Sends appropriate responses such as, for 29 too many requests error. Retry headers indicating when to try again, retry after. Benefits of rate limiting are 1. Prevents abuse, stops malicious clients from overwhelming services. 2. Fairness, ensures equal access to resources for all users. 3. System stability, protects systems from being overloaded. 4. Security, mitigates DDoS attacks and brute force attempts. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com. NoSQL databases are designed for flexibility, scalability, and handling various data types, particularly when dealing with large volumes of unstructured or semi-structured data. They don't rely on the fixed schemas and relational constraints of traditional SQL databases. There are 4 main types of NoSQL databases, each optimized for specific use cases. For more tech interview materials, please go to our website at bowsy8.com. Document stores. How they work. Data is stored in documents, typically formatted as JSON or BSON, binary JSON. Each document contains key value pairs and can have nested structures. These databases are schemaless, meaning documents in the same collection, akin to a table, can have different fields. Key features. Flexible schema for semi-structured data. Supports complex, nested data models. Efficient for reading and writing large volumes of data. Examples: MongoDB, CouchDB. Use cases: content management systems, product catalogs, real-time analytics. Key value stores. How they work. Data is stored as simple key value pairs. The key acts as a unique identifier, and the value can be a string, JSON, or binary object. These databases are highly performant for quick data lookups. Key features: fast reads and writes due to simple data structure. No fixed schema. Ideal for caching and session data. Examples: Redis, Amazon DynamoDB, RIAC. Use cases: caching systems, session storage, real-time leaderboards. Column family stores. How they work. Data is organized into columns rather than rows, and these columns are grouped into column families. Each row can have a variable number of columns. It's optimized for read/write operations across wide datasets. Key features: handles large-scale, time series, and sparse data. High availability and fault tolerance. Efficient for querying large volumes of data. Examples: Apache Cassandra, HBase, ScyllaDB. Use cases: time series data, logging, real-time analytics. Graph databases. How they work. Data is stored as nodes, entities, and edges, relationships. Nodes represent entities, e.g., people, products, while edges represent relationships, e.g., likes, follows. Graph databases are optimized for traversing complex relationships. Key features. Ideal for data with complex relationships. Supports fast traversal of connected data. Uses graph query languages like Cypher. Examples: Neo4j, Amazon Neptune, OrangoDB. Use cases: social networks, fraud detection, recommendation engines. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com.